Hello class, this is lesson 4-8 in our textbook, talking about how to use isosceles and equilateral triangles in a lot of the problems that we're going to be presented with. So I think we know what an equilateral triangle is. That's when all of the sides are exactly the same, they're all congruent. An isosceles triangle is where at least two of those sides are congruent. So in this case, if I have in my triangle two sides that are marked that they're congruent, these two sides are called the legs. So this is a leg and this is a leg. Okay? Where this bottom side that's not congruent to those would be called the base. Okay? Where the two legs meet at the top, this angle is called the vertex angle. And in an isosceles triangle, these two angles at the bottom are both called base angles. And they are actually congruent. So our first theorem is based around an isosceles triangle. So let me show you what I have. It says, for theorem 4.7, that it's called the base angles theorem. If two sides of a triangle are congruent, so if AB is congruent to AC, then the angles opposite them are congruent. What I mean by opposite is if I start with AB, this side, the angle opposite would be this one down here at the bottom, and the angle that's opposite AC would be this one down here at the bottom. So I could write this out. If AB is congruent to AC, then I can conclude that the opposite angles are congruent. So that would be angle ABC would be congruent to angle ACB. Okay. I can actually talk about this information in the opposite direction as well. Theorem 4.8 is the converse of the base angles theorem. And it says if two angles of a triangle are congruent, then the sides opposite them are congruent. So now we're starting with two angles that are congruent. And I can say that if they are congruent, the sides opposite them, so this would be AB, and the side opposite ABC would be the side AC, then those are congruent. So let's write that down. If angle ABC is congruent to angle ACB, then AB is congruent to the other side, AC. So this is some of the facts that we're going to be using for our isosceles triangles. So why don't we go ahead and prove one of these theorems right now. I want us to prove the base angles theorem. And basically what we're given is two sides that are congruent. So in this example, JK is congruent to JL. And I want to prove that JKL, so this top angle, is congruent to this bottom angle, JLK. And let me show you how we're going to do that. We could start by just writing what we're given, okay, that JK is congruent to JL. That those two sides are congruent. And this is given in the very beginning. After that, I'm going to do something on here, and I'm going to draw this point M, which is going to be the midpoint of KL. Okay, so M, I'm going to just draw as the midpoint of KL. This is the definition of midpoint. And then I'm going to connect J and M. And I can just do this because that's the definition of a line connecting two points. So now I'm going to take my ruler to show you this side, JM. Okay. Well, because M is the midpoint of KL, I know that MK is congruent to ML. This is the definition of midpoint. So look here, for these kind of half triangles, I have two sides that are already congruent. Well, I also can see that JM is the same side in both of them. So I can say that JM is congruent to JM by the reflexive property of congruence. So it looks like I have three sides of two different triangles that are congruent to one another. So I'm going to conclude that those two triangles themselves are congruent. This is by side, side, side. And what we learned before is that if two triangles themselves are congruent, then that means that all corresponding parts are congruent. So since I proved that they are congruent, then I can claim that JKL, that this top angle, is congruent to this bottom angle, just simply by corresponding parts being congruent. So I'm just going to say corresponding parts of congruent triangles. And that should be enough of a reason. Okay? I'm going to introduce to you two more corollaries to the base angle theorem. So this is related to an equilateral triangle. And I'm going to say that if a triangle is equilateral, it's also equiangular. Okay? So for instance, if I have triangle ABC, and I know that it's equilateral, meaning that all three of the sides are the same, well, I could prove that this triangle would also have three angles that are exactly the same. And then there's also a corollary to the converse of the base angles theorem. If a triangle is equiangular, then it is equilateral. So if I know all three angles are congruent, then I can also claim that all three sides are congruent as well. So we're going to end with two examples now. Based on all the information that I've just kind of gone through, I want us to find what x and y are in this example. So let's just take it one step at a time. What looks like it would be the easiest? Well, I see right here that this triangle KNL has three congruent angles. So that means it's equiangular. And we just talked about how if it's equiangular, it's also going to be equilateral, which means that all the sides will be the same. So I know that KN is congruent to KL, which means that if KN is y and KL is 4, that y equals 4. That was pretty easy, okay? So then I'm looking down here at this bottom one because I'm just trying to see what it gives me, and it's giving me that these two base angles are congruent, which I know means that it's going to be an isosceles triangle. And so that means that the legs themselves are going to be congruent, which means that LN is going to be congruent to LM. And LM is x plus 1. LN is actually a side of this equilateral triangle at the top, so it's 4 as well. And then if I subtract 1 on both sides, I'm going to find that x is equal to 3. And that's it. It's pretty easy to do, and I think that you guys are capable of doing that as well. The second one that I want us to try to wrap up this lesson is this other triangle right here, and it says to find x and y. But this time, I'm not given any measurements of sides. I'm asked to find some measurements of angles. I am told by the markings, though, of some of the different sides. So let's first look at what we have. This triangle right here is an equilateral triangle because I'm shown that all three of the markings of the sides are the same. And so that means that all the angles are the same as well. So let's see if we can find out what x is. That means if this angle is x, then this one is also x, and this one is also x. So I'm going to do x plus x plus x. All those should add up to 180 degrees. So this is 3x is equal to 180. When I divide by 3, I find that x is 60 degrees. So this means that all three of those angles are 60 degrees. And then since down here at the corner that I'm shown that this is a right angle, I know that both of those angles have to add up to 90 degrees. And I just said that this one right here is 60 degrees. So I need to find out what this little angle is right here. Well, I know that maybe I can just call it Z, okay? 60 degrees plus Z should add up to this right angle of 90 degrees. So when I subtract 60, I find that this is 30 degrees. And since these two legs are the same, this is an equilateral triangle. So that means that this one right here is also 30 degrees. So now I have two of the angles, I can find the y. Y plus 30 degrees plus the other 30 degrees, they should all add up to 180 degrees. So this is y plus 60 degrees. When I subtract, I find that y is equal to 120 degrees. And I'm done. So I hope that these examples have helped you out. We're going to do a lot more work when we get to class, so just let me know if you have any questions when you return.